Welcome to This Explainer. Today we're completely demystifying the optical magic of microscopes. And we aren't just going to sit here and talk about high-level theory, how we bend light to our will, things like that. No, we're actually going to walk step by step through building a working microscope from scratch right on an optical rail. It's going to be a lot of fun. But before we even touch the lab gear, try a quick experiment with me. Hold your index finger out in front of you and slowly bring it closer to your eye. Keep focusing on it. Notice how, at a certain point, no matter how hard you strain those eye muscles, the details of your fingerprint just blur out. That hard biological barrier is literally why we had to invent optical instruments in the first place. Our eyes are just naturally limited. Now, the formal scientific term for that exact blur threshold you just hit, that's called your eye's near point. In physics, this is simply defined as the absolute closest point on which the human eye can comfortably and sharply focus.
And here's the crazy part. Our near point isn't some fixed universal constant. It actually changes drastically as we age. Look at these numbers for a second. If you're a teenager, your near point is incredibly close. We're talking about 7 centimeters. But by the time you're a young adult, that pushes back to around 12 centimeters. And for middle-aged folks, well, the lens in the eye gets a bit less flexible, pushing that near point all the way out to somewhere between 28 and 40 centimeters.
So, because human vision varies so wildly from person to person and year to year, scientists needed a standard. They established a standard observer near point of exactly 250 millimeters, or 25 centimeters. When we calculate how powerful a magnifying lens is, that 250 millimeter mark is the universal baseline we're actively trying to beat. All right, here is our roadmap for overcoming those biological limits. First, we'll look at the power of simple magnifiers. Second, we're building a DIY microscope. Third, we'll tackle image quality and aberrations. And finally, we'll do a commercial objective upgrade. Okay, let's jump right into Section 1, the power of simple magnifiers. So how exactly do we measure a pocket magnifier's power? Well, if you place an object exactly at the focal length of a basic converging lens, the image essentially appears at infinity. That lets your eye muscles completely relax. To figure out the magnifying power, you just take our standard 250 millimeter biological near point and divide it by the lens's effective focal length, or EFL. Moving right along to Section 2, building a DIY microscope. All right, let's actually build our optical bench. First, we align a white flashlight. Then, we mount our test object, a 1951 USF resolution target. Think of this as basically an eye chart for microscopes, originally developed by the Air Force. We're going to center it right on the tiny element labeled 3-1. Next, we drop in our 50 millimeter objective lens. And finally, a viewing screen, exactly 210 millimeters away. The key here: center, target, lens, and screen must be perfectly, absolutely aligned. Now, I want to give you a crucial lab pro tip. Make sure you keep the flashlight at least 10 centimeters away from the target. If you push it too close, the lens is going to project an image of the actual light bulb onto your screen, which completely ruins your view. Oh, and avoid using ground glass diffusers at this stage. They dim the light and lower the spatial frequency, which means those tiny, fine details that your eye's trying to resolve just get lost. With the screen locked firmly in place, we make these tiny, microscopic adjustments to the target's position until the image is crystal clear. Finding this perfect focus is super important because it lets us measure the actual object distance, and that lets us calculate the true transverse magnification, meaning exactly how much larger the image is compared to the real object, rather than just relying on some theoretical math. That brings us to Section 3, image quality and aberrations. To build an actual eyepiece, we take out our screen and replace it with a field stop. That's basically just a tiny 10 millimeter window to block out stray lights. Then, exactly 25 millimeters away from that field stop, we drop in a second 25 millimeter lens to act as our eyepiece. You just gently adjust this whole setup until the image stays a consistent size for your eye. But as you've probably guessed, here is where real-world physics gets a little messy. If you're using a standard LED flashlight, you might see some pretty terrible optical distortions, aberrations that totally blur out the microscopic details of element 46. You can actually fix this by adding a piece of ground glass to soften the light. Just make sure to use a separate holder for it. Stacking it directly against your target will completely ruin your focal planes. Literally, do not stack them. And finally, Section 4, the commercial objective upgrade.
Let's see what happens when we swap out our basic single lens for a commercial 10x objective lens. This one features a numerical aperture of 0.25, which dictates its massive light-gathering ability. We want to see firsthand how modern compound lenses completely solve those messy distortions we just talked about.
Because this commercial lens is incredibly powerful, the physical tolerances are super tight. We have to align to a larger target, set a microscopic working distance of exactly 6.5 millimeters, and place our screen 176 millimeters away. This setup projects a single line pair, just one bright line and one dark line, onto the screen, which lets us physically measure its immense magnification power. So after proving the magnification, we swap our target back to that tiny element 3.1 and reattach our 25mm eyepiece, and when you look through it now, wow. I mean, the image is vastly superior. It's so beautifully corrected by the commercial objective that you absolutely won't need any ground glass to read the highest spatial frequencies. Those distortions we saw earlier, completely gone. By mastering these simple optical principles, calculating near points, carefully aligning lenses on a rail, we literally unlock the entire microscopic universe that's normally hidden behind the blur of our own biological limits. So, equipped with this real-world knowledge of how microscopes actually work under the hood, what tiny mysteries are you going to examine first? Keep exploring, keep questioning, and I'll see you in the next explainer.